So today we are going to study about the structure of hydrogen spectrum. So in front of me is a structure. So first is the spectrum of the hydrogen. We have red color, then we have blue color and violet color. Next is the spectrum of helium, and then is the spectrum of mercury. So these are the different spectral lines we are obtaining, and on a black screen we are obtaining these different spectral lines. So today we are going to study about these spectral lines. What are these spectral lines? So like there were 7 colors in the spectrum of white light, we have the spectrum here of hydrogen atom. So we have studied we are going to study the spectrum of hydrogen atom. So till now we have studied about that the radius of the stationary orbit, or the radius of the orbit which is allowed, is equal to is proportional to the n squared, and we have velocity is proportional to 1 by n. We have found energy is also energy is equal to some constant time. Energy is some constant times 1 by n1 squared minus 1 by n2 squared, and we have also the relation between the wavelength. The most important relation, the wavelength, which color of light will be emitted from the transition, that wavelength will get from this relation. It is equal to Rydberg constant R times 1 by n1 square minus 1 by n2 squared. What is n1 and n2? So we have this hydrogen atom, we have the proton, one proton, and we have one electron, and there are different energy levels. So let this be the radius r1 of the first allowed orbital. Then we have, for this n1 principal quantum number is 1, then for second orbital n is equal to 2, then for third n is equal to 3. So there is a different energy. Let E1 be the energy of first orbital, E2 be the energy of the second orbital, and E3 be the energy of the third orbital. So let the electron be in the third orbital. Electron is in the excited state, and it cannot remain here for more than 10 raised to power minus 8 seconds. So electron cannot remain in the excited state for more than 10 raised to power minus 8 seconds. After this much of time, it has to come back. Therefore, when it comes back, the energy of this orbital is E3, and energy of, now it can come to second orbital or to first orbital. So that we don't know, that is a random phenomena, that it may come to second orbital or it may come to first orbital. But to come, so there are two possibilities. First is that it comes to the first orbital, and second is that it comes to the second orbital. So if it comes to first orbital, then there will be a different lambda. The lambda will be for transition between orbital 3 and 1, as it will release energy in terms of a photon, and the wavelength of photon will be lambda 3.1. And if the transition is from third to second state, then the energy will be related, and lambda will be between 2 and 3. So this will be a different wavelength, this will be a different wavelength. Suppose more energy is released when it comes from third to first orbital, because there is more energy gap, therefore lambda will also be more. And if lambda will be more, so lambda 3.1 will be greater than lambda 2.3. So maybe we find, as we have seen first red color line, so maybe this may be the red color line, and this may rise to the suppose yellow color line. So maybe this transition is for red color line, and this transition is for the yellow color line. So that color of the light emitted, which light will be emitted, which will not be emitted. For example, see, if orange light is not emitted, it means orange light would have been emitted. Orange color is between suppose orange color is between a color which is between yellow and red. But electron is never here. Orange color would have been emitted if the electron has been here and transition has been from this point to this point. But this is not allowed. This is not allowed because this is not allowed. This position is not allowed. Therefore, never that color like orange color will never be emitted in that spectra if it corresponds to this transition. So the spectrum so this spectrum is very specific for an element. The type of spectrum we see for the hydrogen, we will not see that same spectra for any other element. As in the starting picture you have seen, there are 4 different colors for hydrogen. Then there is helium. Then there is the spectrum of helium, so there are certain colors. Then there is a spectrum of mercury, there are certain different colors. So every time you study the spectrum of hydrogen, always those same colors will come. For mercury, always those same colors will come. So if you are studying that spectrum, you can say that that element is mercury. So when we find the presence of elements on another planets or in the space or on the moon, we study the presence of other elements. We are studying the, like we are finding certain presence of certain iron or other element on the surface of the moon or on the surface of the mercury. How we find? We are not taking the element from moon to earth, but we are studying the spectrum of that element. We put a beam of light on the element, we excite that with the electric discharge, and after de-excitation that element emits light, emits radiation. So we study that radiation. So if the spectrum is obtained and then we match the spectrum with the periodic table, all the elements in the periodic table, we have a spectra corresponding to each and every element. So on studying the element, studying the spectra, we can easily say that this is the spectrum of iron or this is the spectrum of hydrogen, and then we identify the substance. For that, the formula is 1 by lambda is equal to Rydberg constant times 1 by n1 squared minus 1 by n2 squared. So very first thing now we have studied the spectrum of hydrogen. There were certain lines. So suppose this is the screen, this is our screen, and we get certain lines here. So suppose very first line, second, third, fourth. First line is maybe red color. In the video also it is red. Then we have green. Then we have blue color, and then we have violet color. If this is the spectrum, no other color will be obtained because only these transition corresponding to these wavelengths are allowed in that atom. So for here lambda is for red color. Suppose lambda corresponds to around 6900 angstroms. So for a green color it is around 4800 angstrom. For blue color it is around 4200 angstroms. For violet it is around 3600 angstrom. So this is a different wavelengths corresponding to the different spectrums of hydrogen. The first line we say as it is H alpha line, H beta line. So we have given names to these lines, H gamma, and then this is H delta line. H alpha lines means it is coming from that particular transition whose energy is corresponding to the red light. Then different, as we have discussed, the transition may be from N1 to from N3 to N1 or N3 to N2, means from a higher level to a lower level, and that lower level may be N1 level or N2 level or N3 level. So according to that level, that from higher level to which lower level the electron will get electron will come, we have certain series. So we have name of certain series. First we have Balmer series. Balmer series. What does Balmer series means? Balmer series means the transition is from any higher level to any higher level to level n1 to n1 level, any higher level to n1 level. Therefore, the lambda corresponding to the Balmer series is lambda corresponding to Balmer series will be r times 1 by, so it is n1 here, 1 by n1 minus 1 by n1 square minus 1 by n squared. And what is n? N is any higher orbital, because the final orbital is n1, so other orbital it may be n, may be 2, 3 or any other higher orbital. So this is the Balmer series. For Balmer series, the transition is from any higher level to the n1 level. This is the Balmer series. The scientist Balmer studied this series. After that, we have another series. So other series we will study. So I have clearly explained what does this transition means. So another series is Paasche series. Second is Paasche series. Balmer series is from higher energy, any higher energy level to level 2. It is not to level 1, it is to level 2, to second level. So this is to the second level is the Balmer series. Then we have Lehman series. Lehman series, the Lehman series is transition from, this is the transition to the ground level. From any higher level to the ground level. So 1 by n1 square minus n to n squared. So here n can be, so n cannot be 1 or it cannot be 2, because transition is always from higher level to lower level. So if the level is 2, the level cannot be, n cannot be 1. Transition can always be from higher level, so n may be 3 or n may be 4 or n may be 5. So here we have Lehman series. So it is to n1 level, so n may be, this n may be 2 or 3 or any other higher level. Then we have Paasche series. Paasche series, so here lambda is, here the transition is to the n3 level. So 3 squared minus 1 by 1 by n squared. And value of n is 3 here. Here the value of n is, so here value of n is 2. So here the value of n is n1. n1 is 1 only, so it is 1 squared. It is 2 squared. 2 squared. Then we have 3 squared is Paasche series. We have bracket series. Bracket series where the transition is from transition to the fourth level of the hydrogen. Transition to the fourth level of hydrogen. And then finally we have Fund series. So in Fund series, the transition is to the transition is to the fourth, is to the fifth level. To the fifth level from any higher orbital. So here n can be 4 or 5 or any higher level because the lower level is 3. Here n can be 5 or 6 because transition is to fourth level. So other higher levels are 5 or 6. Here other levels are 6 or 7 or any other level. These are the different transitions. So we can find, so we will diagrammatically we will write. So note down all these. Now we will discuss it, all the series through the diagram, through one simple diagram. So to make it easy, so this is the hydrogen atom, and so this is the first level, this is the second level. So in this way it is very difficult to tell others level, so many levels, E1 level, E2 level or N1 level, N2 level. So in spite of drawing a circle, we simply draw a line and we say it is a state. So if we draw a state, so this is the first state. Suppose this is our first state and this first state is N1. This is the ground state. and ground state corresponds to the first orbital n1. Then is the second state. Second state corresponds to the second orbital. So this is second orbital n2. In this way, n2. Then we have other. Then we can draw other states as well. The distance between the state goes on decreasing. Distance is also decreasing between the states. The difference between first and second state is maximum. After that, the state becomes, the difference is decreasing. So this we will study in further in more higher classes, that why this distance is goes on decreasing. So n1 it is. So our first is the we have Lehman. Lehman was transition from any higher level to n1 ground level. So any higher level, this is n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, n is equal to 7. So any higher level to this level is Lehman series. So first is it can be from n2 to n1, or it can be from n3 to n1, but the final is n1. Starting may be any higher orbital, but the final destination is the first orbital. So this is our Lehman series. This is our Lehman series, and when the transition is from n2 to n1, there is a photon emitted of wavelength, suppose wavelength lambda 2.1. Then for this transition, another photon of wavelength 3.1. So for this transition, another wavelength of 3.2. So for this Lehman series, it consists of certain colors which correspond to lambda 1 wavelength, lambda 2 wavelength. So this is one spectra, and this series of the spectra is the Lehman series. Next is our Balmer series. So Balmer series is to the second orbital. So it may start from any higher orbital, but the destination is the second orbital. Destination is second orbital. So this is Balmer series. Second is our Paasche series. Paasche is to the third level. So from any higher level to the third level, transition is the Paasche series. Then is the bracket series. It is to the level 4. From any higher level to level 4 is the Paasche series. Lehman, Balmer, Paasche, and this is bracket series. And last is our Fund series from any higher level to level number 5. So any higher level to level number 5 is the Fund series. So these are the different series. So all corresponds to different wavelength, different energy differences, and different wavelength. So these are different series of hydrogen atom which we will get. Lehman, Balmer, bracket, Paasche, and Fund series, which corresponds to the different wavelengths. These are the orbitals. We are not drawing it like in a circular way because it will not be possible to draw so many orbitals on this screen. Therefore, this is a energy state we are representing. Here, the energy is energy, as we have studied the energy. So energy is for hydrogen atom, E1 is equal to minus RHC upon 1. So upon 1 square. E2 is equal to minus RHC upon N squared. So these are the energies. So energy correspond to first level of the hydrogen is minus RHC. To the second level is minus RHC upon 2 squared. Then minus RHC upon 3 squared. Minus RHC upon 4 squared. So RHC upon 5 squared. So these are the different energy. These are the energies, different levels of energies. This equation we have derived in our previous video. Now we are only using these equations to study the spectrum of the hydrogen atom. Now there are certain limitations of the Bohr's theory of atom. So like Rutherford had certain drawbacks which Bohr explained, but still there were certain drawbacks which even Bohr was not able to explain. So note down this, and now we'll study the drawbacks of the limitations of the Bohr's theory. Limitations of Bohr's theory. So limitations. What are these limitations? Very first limitation is it is unable to explain spectra of elements with multi-electrons. Multi-electrons means in which there are more than one electron. Bohr theory explained the hydrogen atom very well. The spectrum of hydrogen it explained very well. But the spectrum of higher elements with more than one electrons, because in the higher there are certain interactions also between the electrons. Electron in the one orbital interacts with the electron in other orbital, but this Bohr's theory was unable to explain. So it explained the spectrum of hydrogen only, or the hydrogen like atoms only. Next is, as we have seen, unable to explain fine structure. So it is unable to explain fine structure, like we have seen here. Here it is red color line, then there is yellow color line or green color line, then is green, then is blue. So like this, when we see, we saw only one line, because our naked eyes, according to the resolution our naked eyes, we can only see one line. How? Because see, there is I have drawn two dots on the circuit, two dots on the board, so you can see the difference between, you can see them as two boards. If I decrease the distance between them, still you can recognize that these are two different dots. But if there is very less difference, now there are two dots. Still I have drawn two dots, but you are unable to see them as two dots. You can only see them as one line, because our eyes cannot resolve more than this. So this is our limitation of our human eye. We cannot resolve more than this. But by using high resolving power spectroscopes, so on seeing this red line by a spectroscope of very high resolving power, we see that this is not one line, this is a band of lines. So this line is also a band of lines. So this is known as fine structure. So this is its structure, and its fine structure is there are further more lines. So Bohr's theory was unable to explain this fine lines. That why red light is further made up of more fine lines. Bohr's theory was unable to explain this as well. So to explain these theories, we have to study the quantum mechanics. So quantum physics we have to study, in which we can see we study the coupling between the electrons, coupling between the orbitals, and that coupling is the reason behind this hyperfine structure. But Bohr was unable to explain this hyperfine structure. Another drawback is relative intensities it cannot explain. So relative intensities. Relative intensities means what is the intensity of red light? red light is more bright than green light, and green light is more bright than the blue light. So there is a intensity difference also. Red light is more bright, it means more transition are happening which correspond to red light. Blue light is not as bright as red light, it means less transitions are there which corresponding to blue light. So why there are more transitions corresponding to red light and there are less transitions corresponding to blue light? This also Bohr was unable to explain. So there are certain other effects also like Zeeman effect, Zeeman and Stark effect. Zeeman and Stark effect. What is Zeeman and Stark effect? That these lines get further splitted in the presence of magnetic or electric field. In presence of electric or magnetic field, the lines gets further splitted. So why the lines get further splitted? So that reason, that is the due to coupling between the external electric or magnetic field and the field of the electrons inside the atom. But that also Bohr's theory was unable to explain. For this also we have to study the quantum physics to study the Zeeman effect and Stark effect. That will give reason behind the Zeeman effect and Stark effect, but not the Bohr's theory, and uh, no explanation or no information about wave nature of electron, about wave nature of electron. So electron is having wave nature or dual nature of particle, wave or wave particle duality. So that the Bohr theory was unable to explain. That also we study in the quantum physics. And the last thing is certain uses of Rydberg constant. So uses of Rydberg's constant R. So what are the uses of Rydberg's constant R? So very first use was to identify the wavelength, to find the wavelength corresponding to transition. So to find the wavelength corresponding to the transition, as 1 by lambda is Rydberg constant times 1 by n1 minus 1 by m2. This was the use. And second use is to find ionization potential, ionization energy. What is ionization energy? So this is the atom, this is nucleus, this is electron, and it is in, suppose it is in some orbit. So in this orbit it has a energy. In the very first orbit it has a energy. How much energy? Minus RHC upon 1 square. This is the energy in the ground state which we have studied earlier. This is ground state energy. And if we want to ionize the electron, ionize the atom means remove this electron from the atom, then when we remove it, its energy becomes 0. The potential energy of the free electron is 0 and potential energy of the atom inside the electron inside the orbital in the ground level is RHC. So how much energy is needed? So this difference is RHC. So RHC, this much amount of energy is required. This much Rydberg constant R is coming here. So RHC amount of energy is required so that an electron can be ejected from the atom, and this is the ionization potential. So for hydrogen atom it is around 13.6 electron volt. So this much electron volt of energy is required to remove an electron from a hydrogen which is in the ground state. So here our this chapter hydrogen spectra is complete. So you please make notes from the video, and any doubt is there that we will discuss in the class.